Okay, two ladybugs are standing on a rotating disc that is spinning counterclockwise. Assume friction between the disc and the bearings on the axle are negligible. Which ladybug has a greater angular speed? Well, angular speed does not take into account the radius at all. Any body on the rotating disc is going to have the same angular speed. They're going to complete the circle in the same amount of time. If you get on a carousel, like at the mall, and you're standing on the outside edge and your friend's on the inside edge, you're going to complete the circle together. You're not going to pass each other. So they have the same angular speed. The ladybug with the greater linear speed will be the ladybug with a larger radius. She has a larger distance to go. Her circumference is larger, so her linear speed is going to be larger. And explaining the difference, or explaining the answer, is just the angular speed does not take into account the radius, where the linear does. So if radius doesn't matter where you are on the disk. Ladybug begins walking in a circular path in the direction of the disk's rotation. How does this affect the disk's the magnitude of the angular momentum of the disk alone? Well, she's walking in the direction of motion, so that means she's effectively moving faster linearly than she was before. Her angular velocity is going to be increased. She's going to complete the circle sooner. If her angular velocity is increased, her angular momentum is larger. Well, if the system has to maintain total angular momentum, if she's increased her angular momentum, the angular momentum of the disk needs to decrease. The only way to decrease the angular momentum of the disk would be to decrease its angular velocity. You can also think of it this way. As she's walking forward, she's applying a backwards torque onto the disk, slowing it down. There's two ways to think about it. I like the first one better because it's using the formulas and the principles within physics. But if you just need to imagine it, the second one works. So now we've got two situations. Ladybug's on the outside edge. She's got a radius of 0.9 r. And then it takes a certain amount of time, 2.5 seconds to make the lap, to complete one cycle, one period. If we were to take that, one revolution is in 2.5 seconds, 2 pi r is the same as one revolution. So now we can get it in terms of, instead of revolutions, we can get it in terms of omega, or radians per second. We're just going to say 2 pi radians is the same as one revolution. Revolutions cancel out. Put this in the calculator. 2 times pi divided by 2.5 would be 2.51 radians per second. This is the omega for Ladybug 1. Ladybug 2, she's moving in much closer to the center of the circle, to the pivot point. Now she is, 0.1 radius. 0.1 r is her radius. And it takes 2 seconds now for it to rotate all the way around. Seems like our period has gotten shorter. Our omega, the time it takes to travel all the way around, angular speed has increased. So one revolution in 2 seconds, one revolution over 2 seconds. And we're going to multiply by 2 pi radian over one revolution, so the revolutions cancel out. That puts us in terms of radians per second. Of course, radians per second is the unit for angular velocity, omega. And we get 3.14. That's the omega for figure 2. Well, if we know initial angular momentum is equal to final angular momentum, we can say I of 1 times omega of 1 is equal to I of 2 times omega of 2. We've solved for the omegas, and then we can set up the problem so that we solve for I2 in terms of I1. So I1 times 2.51 is equal to I2 times 3.14. We're simply just going to divide the 3.14 to the other side. So 2.51 divided by 3.14. 0.8 I1 is equal to I2. While the ladybug is walking towards the center of the disk, does it exert a torque on the disk? No, she's not going to exert a torque because this time the force is going to be in the same direction as the pivot. And so you don't have any torque. It'd be like pushing on the end of the bat towards the batter instead of along the radial line or the moment arm. So the force is being exerted parallel to the radial line. it needs to be perpendicular. All right, back page. We've got a pivot, a point of a pulley. Doesn't indicate that it has any mass initially. Mass 1 on the left, or just 1m. On the right, we have 3m. Draw a free body diagram and determine the acceleration of the system in terms of m. Free body diagrams here, I'm just showing the external torques. The external forces. Yes, tension is going up, tension's internal, so I didn't really mess with that at all. We know acceleration is net force over total mass. In this case, the net external force would be 3mg minus mg, and then the total mass would be m plus 3m. Looking at this, we can easily eliminate the m's. I know it's said in terms of m, but they cancel out. We've got essentially 3g minus g, which is 2g, and then we would have 1 plus 3. I know you canceled out the m, but it was a 1m, so you'd have 2g over 4, which essentially is 1/2 g, or g over 2. How would the acceleration of the system be changed if the pulley has mass? Well, if the pulley has mass, now your effective mass is increased because the pulley is going to resist rotation. And in the place it shows up in the formula is not in the net force. It's not applying a force. It's adding to the mass. Mass in the denominator. Increasing the denominator will decrease your value that you calculate. So I'm just saying that it added mass to the system. Hey, did you know that object moving linearly can have angular momentum? Absolutely, angular momentum is calculated as mass times velocity times radius. The fact that it can hit something and cause the rotation means that there's angular momentum after the collision. There must have been angular momentum before the collision if it's a closed system. Therefore, the object moving in a straight line, if that straight line or its line of action if you can draw a line to a pivot point, that line to a pivot point at 90 degrees will give you the radius, so mass times velocity times radius. And then I'm drawing a little pitiful windmill and then have a little piece of mud flying towards it. Last situation, we've got 4 masses, all have the same mass. All of them are having a force applied to them. 2 of them at 90 degrees, 2 of them at 45 degrees. And we want to know which of the 4 situations results in the greatest angular acceleration due to the force applied. In order to have the most angular acceleration, it's going to come from the most torque. The one on the top left, I'm going to call it number 1. I'm going to number these so that way I can kind of differentiate between each one. Number 1 and number 3 are going to have the greatest amount of force at the same radius. And that is because it's force times radius times the sine of the angle. Here it's sine of 90. Sine of 90 is 1. So number 1 and number 3 have the greatest force. But number 1 and number 2 have the lowest rotational inertia. They all have the same mass, but the distribution of mass matters. By pushing the mass to the outside edge, you're going to treat it more like a ring. I is mr squared for a ring, where 1 and 2 are more like a disk, and it's just 1/2 mr squared. So 1 and 2 have the smallest rotational inertia, or I, and 1 and 3 have the highest force. So number 1 has the highest torque with the lowest rotational inertia, so it's going to have the most angular acceleration. Derive an equation to calculate the angular acceleration of the object. Moment inertia is I. F is force, and you know it's 45 degrees. Well, I know that torque is equal to I alpha, or rotational inertia times rotational acceleration. So if we start with T is equal to I alpha, divide the I to the other side, and alpha is torque over I. And here we're saying torque is force times radius times the sine of theta, theta being 45. So alpha is equal to F times R times sine of 45 over I.